Have you ever, found yourself talking to an AI chatbot and it feels surprisingly real?
Yeah.
Or maybe just seeing those self-driving cars trying to handle like a really busy street?
Yeah, it's becoming kind of hard to ignore.
Exactly. From the quick suggestions popping up on your phone to even complex medical stuff being assisted by machines, deep learning is just, it's quietly powering so much. It really is everywhere.
And it seems to be getting more powerful faster than almost anyone really expected.
It's this huge technological leap, isn't it? It's reshaping whole industries, even how we think about intelligence itself.
Absolutely. And you might be asking, okay, how did this tech get so powerful so quickly? What's actually happening, under the hood that lets these systems do such amazing things?
That is precisely what we're getting into today. In this deep dive, our mission is to unpack the core ideas behind deep learning. We'll explore its current applications, the ones really changing our world, like those AI assistants and the promise of autonomous cars.
And then we'll also need to look critically at its limits, right? And the bigger societal questions it brings up.
Exactly. The goal is for you to walk away with a really clear picture of what's happening at the sort of cutting edge of AI right now.
And to help us navigate this, we've got some great source material. We're drawing on the 100-page machine learning book for that solid, foundational understanding. It's clear, technical, but doesn't, get totally lost in the weeds.
Right.
And then for insights from some of the actual researchers, the pioneers, we've got Architects of Intelligence. It offers really diverse, sometimes even conflicting views on where this whole field is actually going.
Perfect. Okay, so let's pull back the curtain. Deep learning. This is the term everyone uses almost synonymously with AI.
Yeah.
But what is this thing, really? How does it actually learn?
Well, at its core, deep learning is a specific type of machine learning, and machine learning itself is a branch of artificial intelligence. The simplest way to think about machine learning is maybe computers programming themselves, instead of a person writing out every single rule for every possible situation.
Which would be impossible for complex tasks.
Totally impossible. Instead, these algorithms learn patterns directly from massive amounts of data.
Okay, and the deep part, what makes it deep? Is that neural network thing mimicking the brain just a nice analogy, or is there more to it?
That's a really good question. The deep refers to the structure, these deep neural networks. They have many layers, sometimes hundreds, of what we call simulated neurons or units.
Yes, you live in neurons, okay.
And yeah, while they're definitely not exact copies of biological neurons, they are roughly inspired by the structure and interaction in our brains. It's an idea that, surprisingly, goes way back to the 1950s.
Wow, the 50s. So if I'm trying to picture this network, is it like a super complex electrical circuit? Information flowing through?
That's a pretty good analogy, actually. Imagine you have input values, like, say, all the pixels from a photo of a handwritten number. These values flow through multiple layers of this circuit.
Okay.
At each layer, new values get calculated based on connections between these units. And those connections have weights. They determine how much influence one unit has on the next. Eventually, this process leads to an output, like a prediction. That number is an 8.
Right, the prediction. And I keep hearing about nonlinearities being absolutely vital for deep learning. Why is that specific thing so important?
Ah, yes, nonlinearities. This is sort of where the magic happens. Think about it like this. If you only used linear functions, straight lines basically, no matter how many layers you stacked up, you could only ever approximate simple linear relationships, like trying to draw a curve using only straight rulers.
You couldn't capture complexity.
Exactly. Nonlinearities allow the network to bend, to twist, to learn incredibly complex, wiggly patterns that exist in real-world data, like the subtle differences between faces or the nuances of language. Without them, deep learning wouldn't be nearly as powerful. It's a fundamental piece.
That makes sense. So this complex circuit with its curves can learn intricate patterns. But how does it learn them? How does it figure out what a cat looks like or how to translate French to English?
Okay, so the main way, especially for tasks like image recognition or translation, is called supervised learning.
Supervised, meaning humans are involved.
Heavily involved, at least in preparing the data. It requires enormous data sets where every single example is labeled by humans. So it's not just a million cat photos, it's a million photos, each explicitly tagged with the label cat, or boat, or Dalmatian dog.
Okay.
These labels act as a supervision signal. They tell the network what the correct answer is supposed to be for each example, guiding its learning process.
So it makes a guess, checks against the label, and adjusts itself if it's wrong. Kind of like trial and error.
Pretty much, yeah. You can see the basic idea in the original perceptron. The simplest possible neural network, just one simulated neuron. Imagine trying to teach it to recognize a handwritten 8.
Okay.
It adjusts its internal weights, how much importance it gives to different parts of the input image, and a threshold for firing. If it guesses 8 and it is an 8, great. If it guesses 8 and it's actually a 3, it tweaks those weights a little bit, trying to do better next time. It's a gradual refinement, like how pigeons in experiments learn over many trials.
And with deep networks, with all those layers and weights, how does it efficiently figure out which weights to tweak and by how much? That sounds incredibly complex.
That was a huge hurdle for a long time. The solution is an algorithm called backpropagation. It's really the key algorithm that made training deep networks practical.
Backpropagation.
Yeah, think of it like this. When the network makes an error on its final prediction, backpropagation calculates how much each connection in each layer contributed to that error. It works backward from the output layer, figuring out the blame for the mistake.
So it traces the error back through the layers.
Exactly. And then it adjusts the weights in each layer accordingly, nudging the whole network towards making better predictions next time. It was a massive breakthrough.
Okay, so we have this basic idea of a neural network learning through supervised data and backpropagation. But you mentioned different kinds of data, images, text, sequences. Do we need different types of networks for those?
Absolutely. The architecture matters a lot. For computer vision, for understanding images, the dominant approach is convolutional neural networks, or ConVin.
Convents, right.
Jan LeCun was a key pioneer here. Convents are designed to process grid-like data, like pixels in an image. They work by learning hierarchies of features.
Hierarchies, what do you mean?
Well, the first layers might learn to recognize simple things like edges or corners. The next layers combine those to detect shapes or textures. And layers deeper still might combine those shapes to recognize complex objects like faces or cars or, cats. It mirrors how our own visual cortex seems to work, building up complexity.
Fascinating. Okay, so that's for seeing. What about language? Text or speech, where the order of words is crucial.
For that kind of sequential data, we often use recurrent neural networks, or RNNs.
Recurrent, meaning they loop back somehow.
Exactly. RNNs have connections that loop back on themselves, allowing them to maintain a sort of memory of previous inputs in the sequence. Think about understanding a sentence. You need to remember the beginning of the sentence to make sense of the end.
Right. Context matters.
Precisely. Standard RNNs had some limitations with longer sequences, but newer versions like LSTMs and GRUs use clever gated units that help them decide what information to remember and what to forget over time. This memory is vital for tasks like machine translation or generating coherent text.
That makes sense. Memory for sequences. And then there's another one you hear about, reinforcement learning. That sounds quite different, maybe less reliant on those huge labeled data sets.
It is a different paradigm. Instead of learning from labeled examples, a reinforcement learning agent learns by trial and error, interacting with an environment.
Like training a dog with treats.
That's a perfect analogy. The agent performs actions, makes moves in a game, say, and occasionally receives rewards or penalties from the environment based on those actions. It learns a policy, a strategy, to maximize its cumulative reward over time.
Where is that used mainly? Games.
Games are a classic example, like teaching an AI to play Atari or Go. But the principles apply elsewhere too. For really complex problems with huge numbers of possible situations or states, instead of using simple lookup tables like old-school Q tables, reinforcement learning often uses deep neural networks to approximate the value of different actions or states. That's how systems like AlphaGo got so powerful.
Okay, wow. So we've got the basic machinery. Supervised learning, backpropagation, specialized networks like ConNets and RNNs, and even reinforcement learning. Now let's see this stuff really working. Where is deep learning making the biggest waves right now? How is it powering everything?
Oh, it's undeniable. It really is the primary technology that has powered the AI revolution over the past decade or so. You see it everywhere. Well, every single major tech company, Google, Meta, Microsoft, Amazon, Apple, and also giants in China like Baidu and Tencent, they've invested billions and are using deep learning across pretty much all their products and services. It's even driving hardware innovation companies like NVIDIA and Intel are designing chips specifically optimized for these deep learning calculations.
So it's foundational now. Let's talk computer vision.
Yeah.
You mentioned convnets. How good are computers at seeing now?
The progress has been genuinely staggering. The real turning point, as many see it, was the ImageNet competition back in 2012.
ImageNet.
Yeah, it's a massive data set of labeled images. In 2012, a deep convent just blew away all the previous approaches to object recognition. It was a combination of the deep learning algorithms, those huge data sets, and crucially, the processing power of GPUs that finally unlocked this level of performance.
And that led to things like image captioning, where
Right.
the AI describes a picture.
Exactly. Systems like Google's Show and Tell or Microsoft's Caption Bot, they can look at an image and generate a sentence describing it, like a group of people playing frisbee in a park.
Which is amazing.
It is amazing, but they also make mistakes, sometimes hilariously nonsensical ones. It shows they're great at picking up statistical correlations between pixels and words, but they don't understand the scene in the way a human does. There's no real-world knowledge behind it.
Right. Still a gap there. What about understanding language NLP? Speech recognition, for example. It feels pretty good on my phone most of the time.
It's definitely got much better. For everyday speech in relatively quiet conditions, it's probably around 90–95% of human accuracy, which is remarkable.
But it still messes up sometimes, right? Especially with noise or weird phrasing.
Oh yeah, background noise is a killer. And it struggles with ambiguity, or things that require real-world understanding. The classic example is hearing recognize speech versus recognize speech. Or like understanding the difference between moose the animal and mouse the dessert based purely on context that requires understanding, not just sound patterns.
Yeah, good point. And translation. Google Translate seems almost magical sometimes now compared to a few years ago.
That's largely thanks to the shift to neural machine translation, which really took off around 2016 with Google's big rollout. These systems look at the whole sentence or even paragraph context using those RNNs we talked about.
And that made a huge difference.
Huge. It really bridged the gap significantly towards human-level translation quality for many language pairs. But again, it's not perfect. It can still produce cryptic or nonsensical translations, especially with idioms, subtle humor, or very technical text. It's a sophisticated pattern matcher, essentially.
Yeah, okay. And speaking of understanding language, what about question answering? I remember IBM's Watson winning Jeopardy. That felt like a massive moment.
Watson was definitely a landmark achievement and captured the public imagination. It was brilliant at parsing the tricky Jeopardy clues, searching its massive database, basically all of Wikipedia, and finding the answer.
But was it truly understanding the questions?
That's the debate. Some researchers argued it was more of a specialized system, a parlor trick almost, optimized for Jeopardy's specific format and relying on identifying patterns in the clues rather than a general AI that could understand and reason broadly. Impressive engineering for sure, but maybe not a leap towards general intelligence in itself.
Gotcha. And then the big one everyone talks about, self-driving cars. How much is deep learning the key there?
It's absolutely central. Sophisticated computer vision, powered by deep learning, is essential for recognizing lanes, traffic lights, signs, pedestrians, other cars, cyclists, everything.
But we don't have them everywhere yet. The timelines seem to keep slipping.
Yeah, some of the early predictions were definitely unrealistic. Getting a car to drive reliably in a limited, mapped area geofenced autonomy that seems relatively soon. But general, drive anywhere, anytime, self-driving. Most experts think that's still multiple decades away. The number of unpredictable edge cases in the real world is just immense.
Makes sense. It's not just consumer tech, though, right? Deep learning is making inroads in science and medicine, too.
Oh, absolutely. It's having a significant impact, often behind the scenes. For instance, in drug discovery, companies like In Vitro are using machine learning on vast biological data sets to try and predict which drug candidates are likely to succeed, potentially making the process faster, cheaper, and more successful.
That could be huge.
And it's being used to help doctors analyze medical images like X-rays or MRIs to spot signs of disease, sometimes even better than human experts in specific narrow tasks. Plus, it's improving scientific modeling in areas like climate science.
Okay, one more area. Games. They've always been a test bed for AI. Deep learning seems to have conquered games like chess and Go.
Yeah, games provide these perfect little microcosms for testing AI ideas. Chess was largely solved by brute force search, but Go, with its complexity, was different.
AlphaGo. Yeah.
AlphaGo was the breakthrough. It used deep learning combined with reinforcement learning, learning largely through self-play, playing millions of games against itself. It beat the world's best human players in a way that seemed almost intuitive, making moves that commentators described as beautiful or even miraculous. It really showed the power of these techniques.
Okay, so Deep learning is undeniably powerful. It's reshaping so much, but it's not perfect. It's an unfinished symphony, as you put it earlier. What are the biggest limitations we need to understand?
Yeah, it's crucial to see the boundaries. One of the biggest is its major limitation, that incredible hunger for data, specifically massive quantities of human-labeled data.
Unlike us, humans can learn from just one or two examples sometimes.
Exactly. You see one giraffe, you know what a giraffe is. A deep learning model might need thousands, maybe millions, of labeled giraffe pictures to get really good. This difference points to something fundamental,
Which is?
which is related to transfer learning. Humans are amazing at taking knowledge learned in one context and applying it to a completely new, different situation. Current AI, especially deep learning, is generally terrible at this.
So the learning is very specific, very narrow.
Often, yes. Researchers like Gary Marcus argue that deep learning solutions can be extremely superficial. He gives examples like a game-playing AI that achieves superhuman skill, but if you just shift the paddle position by a few pixels, its performance completely collapses.
Because it hasn't learned the concept of hitting a ball with a paddle, just the pixel patterns.
Precisely. Or AlphaGo, brilliant at the standard 19 by 19 Go board, but it couldn't play on a slightly different sized board without completely retraining from scratch. It highlights a lack of deeper, more abstract understanding.
So this ties into the common sense problem, the lack of real understanding.
Absolutely. That's probably the biggest barrier between current AI and anything resembling human-like intelligence. Deep learning excels at statistical learning, pattern recognition, large-scale data analysis, but it doesn't really get below the surface. It doesn't build world models or understand cause and effect in the way we do.
Are there specific tests that show this limitation?
Yeah, one interesting example is Bongard problems. They're visual reasoning puzzles that require abstraction and analogy making. Humans can usually solve them quite easily, even with just a few examples, but ConNets, they struggle immensely, even after being trained on like 20,000 examples.
Wow.
It makes you think about what intelligence really is. Douglas Hofstadter expressed this kind of philosophical terror, his fear that maybe qualities we think are uniquely human, like creativity or even consciousness, might turn out to be disappointingly simple to mechanize if AI continues to progress in certain ways.
That's a heavy thought. Okay, what about other issues? Security. Can these systems be tricked?
Yes, and this is a really practical concern. It's called adversarial attacks.
Adversarial attack.
Yeah. Researchers discovered you can make tiny, often human imperceptible changes to an input, like subtly altering pixels in an image, putting a specific sticker on a stop sign, maybe even slightly modifying an X-ray image.
And the AI gets it wrong.
Not just wrong. It can be fooled into making a completely wrong prediction with extremely high confidence. A picture of a panda might be confidently classified as a gibbon with just a tiny bit of engineered noise added.
Whoa. So for self-driving cars or medical diagnosis, that's a huge risk.
It's a massive risk. It again highlights that these systems don't really understand what they're seeing in a robust human-like way. They're recognizing statistical patterns, and those patterns can be manipulated.
Okay, so clearly, deep learning, as powerful as it is, isn't the same as artificial general intelligence or AGI, that sci-fi idea of a truly thinking machine.
Definitely not. It's crucial to make that distinction. Deep learning is just one tool in the toolbox, a very powerful one, but it's not synonymous with AGI. AGI implies human-level cognitive abilities across a wide range of tasks, the ability to reason, plan, learn efficiently, understand context. We're not there.
And the timelines for AGI, people seem all over the map on that.
Wildly different predictions. You've got people like Ray Kurzweil who believe in exponential progress and predict AGI relatively soon, maybe 2029. Then you have roboticists like Rodney Brooks, who are much more cautious, suggesting maybe 2200 or even later. It highlights this tension between maybe the engineer's pessimism about the sheer difficulty of the remaining problems and a belief in accelerating technological returns.
So AGI, if it happens, will likely require more than just bigger deep learning models.
Almost certainly. Most researchers believe AGI represents a series of other hills to climb. We need fundamental breakthroughs beyond just scaling up current deep learning, especially in areas like common sense reasoning, causal understanding, unsupervised learning, and learning from far less data.
Okay, let's shift to the broader societal impact. Jobs are always a big concern with AI. What's the realistic picture there?
Well, the sources suggest it's a mixed and complicated story. Yes, jobs involving highly repetitive tasks, both physical and cognitive, are definitely at risk. In many cases, humans are currently acting like robots, so when the actual robots or AI get good enough,
Those jobs might disappear.
they might. But the narrative also stresses that new jobs will be created, jobs managing AI, designing AI systems, jobs we can't even imagine yet. And many existing jobs will change, requiring people to work alongside AI.
So adaptation is key.
Absolutely. The need for widespread retraining programs and a shift towards lifelong learning becomes really critical for individuals and society to adapt.
And what about bias? We hear a lot about AI systems inheriting human biases.
That's a huge and really important issue because these systems learn from data, and data often reflects existing societal biases, racial, gender, economic, et al. The AI can learn and even amplify those biases. This can have fatal implications in areas like loan applications, hiring, or criminal justice.
Can we fix it?
Well, the challenge is significant. But interestingly, one perspective offered is that it might ultimately be a lot easier to reduce bias in a machine than it currently is with people.
Oh, so.
Because with an AI system, you can, in principle, audit the data, examine the algorithms, test for biases systematically, and try to correct them. Debiasing human decision-making is arguably much harder, dealing with subconscious factors. It's not easy, but maybe more tractable with machines in the long run.
Interesting point. What other societal risks come up? Power concentration, privacy.
Yes, those are mentioned too. There's a concern that AI could further concentrate power in the hands of large corporations or governments that have the data and resources to develop and deploy it. Facial recognition technology is often brought up as a key example here, with its obvious privacy and surveillance implications.
And autonomous weapons. Sounds pretty scary.
It's a very serious debate. Concerns range from the ethics of machines making life or death decisions to the potential scalability. Could cheap, autonomous drones become weapons of mass destruction? There's a strong call in the materials to focus on regulating the applications of AI, particularly in weapons, rather than trying to regulate the research itself, since AI is such a general-purpose technology.
Right. Regulating use, not discovery. And finally, this idea of the control problem or alignment, the fear of superintelligence turning against us.
Ah, the alignment problem. This is where things get quite philosophical, even speculative. You have thinkers like Nick Bostrom who are deeply concerned that a future superintelligent AI might develop goals that conflict with human values, potentially posing an existential risk.
Yet not everyone agrees it's an immediate concern.
No. Others, like Andrew Nang, are more pragmatic, suggesting it's like worrying about overpopulation on Mars. An interesting problem for the distant future, perhaps, but not the most pressing issue compared to challenges like bias, jobs, and security today.
It's a question of aligning AI with human values, but we don't even fully understand our own values.
Exactly. How do you program human values into a machine when we can't even agree on them ourselves? It's a profoundly difficult question, maybe the ultimate long-term challenge if AGI ever becomes a reality.
Wow. Okay, this deep dive has covered a lot of ground. We've seen the incredible power of deep learning today, how it's in our phones, helping doctors, driving towards autonomous systems.
And we've explored how it works, those neural networks, the learning process, the different architectures.
But we've also seen the clear lines, the difference between this powerful but narrow AI we have now and that far-off goal of true artificial general intelligence.
Yeah. It's an amazing tool, evolving incredibly fast, but it's fundamentally different from human intelligence in key ways: that data dependency, the lack of robust common sense, the brittleness.
So to leave you, our listener, with something to think about.
Yeah.
Given these current limitations, especially that lack of real understanding and common sense, how do you see our relationship with AI evolving in the near future? Will we just keep adapting to the machines, learning their quirks, working around their limitations?
Or is it possible that future breakthroughs will finally allow machines to truly understand and adapt to us, maybe in ways that feel much more profoundly human? Something to chew on.